Welcome back. This is the end of chapter 3. We have 2 more sections, and we're just going to do one example. This is a very short thing. What we're looking at for section 3.10 is what's called a linear approximation. The idea is that we have a curve, and if we could instead, for x values that are very close to our a value that's down here on the x-axis, right here, if we could use a straight line instead of the function itself, that'd be a whole lot easier to calculate, if you understand, because a straight line is a whole lot easier to mess with. And so this is an introduction to the idea of using a different function to represent a function. And the reason that we would want to do that is because if we can evaluate a function using a polynomial, which is very easy to take the derivative of and so on, then we would rather deal with that where we can get approximations there. And here's the idea. We are going to use an equation of the tangent line. That's going to be our y minus y1 equals m times x minus x1. And this can be rewritten as y minus f of a being, again, our x value of choice. And that's going to give us m, which is f prime of a, and then x minus a. And this is the whole idea. And when I solve for y, I'm going to end up with f of a plus f prime of a times x minus a. And that is going to be what's called our linear approximation. Linear approximation. And it's also referred to as the tangent approximation. Of f of x at x equals a. In other words, again, as we're interested in what's happening at a here, we would rather use our linear approximation line if possible. And here's our actual formula here. This is the tangent line, tangent approximation. And so officially, instead of using y or f of x, we often use, for the linear approximation, we use L of x. And this is, again, f of a plus f prime of a, which is our slope, and then x minus a. This is the linearization. Again, of f of x at x equals a. So let's actually do an example. So here we have the function. You can see the blue here is y equals the square root of x plus 3. And we're going to come up with the linearization to approximate 3.98 and 4.05. So let's get started. So first of all, at x equals a, which is 1 in this case, let's see what we actually get. So f of 1 is the square root of 1 plus 3, which equals root 4, which is 2. So we're looking at the point 1, 2 that we're interested in. And so we're going to have to go ahead and take the derivative of this. So f of x equals our function here. I'm going to write it like this, to the 1/2, which is from the square root. So f prime of x is going to be 1/2 x plus 3 raised to the negative 1/2 power. And when I plug in f prime of 1, I get 1/2 times 1 plus 3 to the negative 1/2 power. Now, keep in mind, this is 1/2 times, and the square root comes down here now, that's root 4. Root 4 is 2, of course, which means our slope is 1/4. So let's create our line. Y minus our y value, which is 2 here, equals the slope 1/4 times x minus 1. So what we're saying is that this is our linearization. This is our 2 plus 1/4 x minus 1. And this is our approximation only when we're very close to a equals 1 of the square root of x plus 3. And we're going to demonstrate that. So to get the square root 3.98, which I'm going to go ahead and do real quick, the square root 3.98. This is about 1.995, we'll say. And what I'm saying is when we plug in this, now you'll notice that we need to plug in to get this, x is going to have to be 0.98, right? Because we're adding 3 to that. So when I plug in 0.98 into my linearization, I'm going to get 2 plus 1/4 of 0.98 minus 1. And let's see if we get something close to 1.995. Guessing we will. 2 plus, I'm going to use with the glare there. I'm going to use 0.25 for the 1/4, 0.25 times 0.98 plus, I'm sorry, minus 1. Minus 1. Look at that, how close that is. 1.995. Now you'll recall right here that it wasn't exactly that, but it was close. And let's go the other way. So for the radical down here, let's do a different color. For the radical 4.05, which is about square root of 4.05. That is 2.012, about. And let's see what happens when we do the linearization. Now, to get 4.05, plugging it into here, or into our function, I'm going to have to make x is going to have to be 1.05, because 1.05 plus 3 is 4.05. So that's what I'm going to plug in to my linearization. And I really should box my linearization just to make it clear where I'm plugging that in. So that's going to be 2 plus 1/4 of 1.05 minus 1. Let's see what we get. I'm going to use 0.25 once again. So that's going to be 2 plus 0.25 times 1.05 minus 1. And look at that. Pretty darn close. So it's not exact, but it's pretty close. And that's what linearization is about. We'll talk more about this when we hit chapter, when in Calculus 2 next semester, when you get to chapter 11 with the Stewart book, where we do a lot of rewriting functions as easier to manipulate functions. I hope that helped.